All right, so what we'll do now is we're going to take a look at the handwriting database, okay? So this is kind of the classical real application of neural networks, okay? And this is the MNIST database of handwritten digits. We have 60,000 examples and a test set of 10,000 examples. And all of these, let's see if we can find some images here. All of the images have been kind of cut into these nice little, there's a single 28 by 28 grid, okay, and a thing of 28 by 28 pixels, and there's a number written there, okay? And this was in order to kind of train, I believe it was postcard or handwritten zip codes. So this was the post office. They wanted to say, can we get away so people don't have to read the zip codes, but we can have a machine read the zip codes. So this was the technology being used to develop that. And so yeah, they scanned all of these things in, made these 28 by 28 pictures, and that database is available for us here. Okay, if you want to use this, you gotta you download this, and then you have to get it into R. And so luckily this person wrote a package or wrote a function to read in this binary data, okay? And then apparently these are different different ways of classification and stuff. Okay, and then so to load the data, we'll do that, and we'll load the data. Okay, so now my data is loaded, and we'll try let's just see, show digit. Oops. AR784. Okay, so let's do I'll do train $X, and we'll just do the first row. Okay, this is kind of our first observation here, and right now, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so just the nature of this is if I expand my console window, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5. Okay, I just need to make it a little bit wider. 1, 2, 3. Is that going to do it? You can actually start to see the image itself. Let me see. One more. So if I do this, okay. So this is the first image, okay, and here you can see everything's we have a 28 by 20, it's 784 values in a single vector, but here I've arranged it basically into a 28 by 28 thing, and because the zeros appear pretty much blank, and then when there's a dark number, it's on a 0 to 255 scale, so the darkest gets indicated here with like 253. That shows up there, okay? So this is kind of the first one, and we can see, oh, that kind of looks like a 5, and here is a this looks like a 0, okay? And effectively, this is what we have, and but probably it makes more sense to use the show digit function, which I think of train $x1 here, and okay, so that's one value, and here's another one being plotted. Okay, but so this is when it plots it, but really it's just a vector of 784 values. Okay, so what we will do is we will develop the same neural network structure that we had in the last time, except we will have 784 values in our input layer. Okay, we have one value for every single one of these pixels. There's 784 pixels that will go into our input layer. What we will have is we will create a hidden layer, and depending on which your structure, I guess we'll save that. That's fine. So we'll take, we have our input layer. There's going to be 784 of these things coming in. One for each pixel. And I'll create a hidden layer, and you can do different things. I'll put 150 nodes in the hidden layer. Okay. Okay, and so you can imagine all sorts of lines coming in here. All right. And then for our output layer, we will have just 10 nodes. Okay, we will have an output for each digit: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Okay, and this will be our going from the hidden layer to the output layer. That's what we've got. Okay, so we have weight matrix 1 will be 784 by 150, and weight matrix 2 will be 150 by 10. Okay. For the output layer is that, let's say this is our right, and then we've got some kind of digit here in our pixels, something like this. Okay, so we've got different values here, and this will be classified. This is seen as a 4, right? So the output layer should report back that as far as the digits go, we're going to have 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, or maybe maybe the first digits is 0. Maybe I start counting at 0 and I go to 9, or maybe I start at 1 and I count to 0. I don't know. So one way or the other. We just have to be consistent as we go. It's an arbitrary thing, right? Okay, so this is I guess I'm sorry. Our output layer we will start our counting at 0. Okay, so the first node will be 0, and then the last node will be 9. So I guess if it was 4, so this corresponds to 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so we'll have something like that, and this is 28 by 28 pixels. So 784 values on the input space. We've got our first weight matrix, and then we'll have our second weight matrix. Okay, and then in this place, we will add biases. Okay, so let's do our kind of our forward propagation, just to make sure we have everything. So we have x. X is n by 784 multiplied by our first weight matrix, which will be 784 by 150, and this will be z, and so our result here will be n by 150. Okay. What we'll do now is we will add a bias matrix. So I have n by 150 here, and I will add a bias matrix, kind of our first bias matrix. I guess I'll call this B1, and this will be also n by 150. All right. So we'll add z, and all the bias matrix does is, if you think about our sigmoid function, all it does is it just, adding a bias will shift it one way to the left or to the right. Okay. And so here we apply the function, the sigmoid function. F of x is sigmoid function. And this will produce our set of activations at the kind of our second layer, n by 150. All right. And then once we have this, we will take our activations, and we will multiply that by our second weight matrix. So here I've got n by 150. Our second matrix will be 150 by 10, because we've got 10 in the output layer. And so now I've got n by 10 values here. And then lastly, we will apply the function to this plus a set of biases. So here I've got n by 10, and then also n by 10. Okay, so we can add these, and this will be our predictions y hat, which will be n by 10. Okay, but keep in mind the B1 as a matrix is really just the same 150 values repeated n times. Okay, because we don't want different biases for each observation. We want the same biases, and there's 150 of them. We wanted them repeated for all n observations. And same thing here, okay? It's the same 10 biases, bias values repeated n times. So that's what we have there. Okay. To train the network, so if we look at this, we've got tons of parameters to estimate, right? 784 times 150, I don't know what that is. That's a lot, okay? We've got a ton of parameters to estimate, and yeah, I don't know. We're gonna have to figure something out here, and so what we'll do is we're going to again just use gradient descent. Okay, so the gradient descent worked when we had 9 parameters to estimate. Gradient descent will also work now that we have, I don't know, several thousand parameters to estimate. Okay, maybe I shouldn't do 150 is probably way too many nodes to have in the middle, but it doesn't matter. Okay. So, we could do 30 or 50 or something like that, okay? But anyway, we've got a punch, and what we'll do is we're going to do gradient descent. Now, when we do gradient descent, however, we had, there's 60 in our trainings data, okay? So, again, so we'll use gradient descent. to minimize the loss function, which will be, again, kind of the squared residuals, which y minus y hat squared. Okay, and then now we have to find what happens. Okay, so we have to find the gradients for both weight matrices and both bias matrices. So we'll have to find the gradient with respect to weight matrix 1, the gradient with respect to bias matrix 1, the gradient with respect to weight matrix 2, and the gradient with respect to bias matrix 2. Okay, it's not too terrible. Okay, but it is a lot. It is a lot that we've got to figure out. Okay, so all right, and then when we do this computationally, though, keep in mind our training set has 60,000 rows, right? And so if we do, if we try to do it, like the computer could handle it, but if we do, n times 784, and our n is 60,000 by 784, this is a massive matrix, and it could bring our computer down to its knees. So what we want to do is we're going to do something called stochastic gradient descent, okay? And so this is basically, you know what, let's not do the entire 60,000 training sets all at once and repeat. Let's just take a chunk of these, maybe 10 rows at a time, and use those 10 rows to use the cost function applied to those 10 rows to help improve our weights, okay? And so, yes, we could look at all 60,000 rows, and basically all 60,000, each row would say, you know what, if you want to improve the weights, go in this direction, and another row will say go in this direction, and another one will say go in this direction. And then what you do is you just kind of, with the gradient, you just take all of those directions and you add them together, and you just get one direction, which is kind of an average of all of those things. But what we can do is we can just say, all right, let's do 10 at a time, and we'll just try to improve the weights according to 10 at a time. So we will split up the 60,000 rows into 6,000 mini training sets of 10. Okay, the selection of 10 is arbitrary. If you want to do rows 20 observations at a time, 100 observations at a time, that's fine. Okay, and so this is called stochastic gradient descent, because the selection of 10 rows is random. Okay, stochastic gradient, so stochastic means there's some kind of random process in there. Okay, so choose 10 rows at random, 10 random rows, okay? And what we might do is we might just shuffle up the 60,000 rows and then just break them into 6,000 chunks, and we'll just go through each chunk. So choose 10 random rows, and then we'll find the gradient with respect to those 10 rows, or find the gradient based on these 10 rows. And then we'll take a step and in the opposite direction of the gradient. Okay, and then and we repeat. Choose another 10 random rows, do that, and we'll do that. Okay, so that's what we'll do for our data set. So we'll load this up here. Yeah, let's look at one of these things. The label is 0. We look at this. And we do show digit. Show digit J. Okay, so the label is 0, and that's what it looks like. Okay, so that makes sense. Okay, what I'm going to do is I'm going to turn those labels from into kind of a vector of this. And so if I do this, I will, I'm going to just apply the vectorized function to y. So basically, if I call function vectorize on 0, it will put 1 at the first thing and 0s elsewhere. And if I call vectorize on 3, the fourth value will be 1 and everything else will be 0. Okay, and vectorize on 9, everything's 0 except for the last one. So this is the function vectorize. It just takes a vector of 10 zeros and changes one of them to 1, and it returns that. Okay, and I'm going to apply this to right now train $y. Let's just take the first few of these. These are the values 5, 0, 4, 1, 9, 2. Those are the labels on the first 6 entries here. Okay, so I'll apply this, and it does seem to be correct. So we have 5, 0, 4, 1, 9, 2, and that makes sense. Okay. Yes.
So you're reducing it to one-hot vectors so that you get 10 nodes as your output that are all zeros or ones. Why wouldn't you just reduce it down to 1 that's 0 through 9?
Yeah. So the way we're doing our cost function, right? We're taking the squared residuals, right? And so if we say, you know what, we want to, if it's a 9, okay, so we're going to scale it from 0 to 1, right? And so if it's a 9, it will have a value of 1. If it's a 0, it has a value of 0. If it's 1, it's going to have a value of 0.1 or something like that, right? Or I don't know, 0, 0.1, 0.2, 0.3. And the problem with that, it's an okay way, but the problem with that is that if the true value is a 4 and it guesses a 5, the penalty there is a lot smaller than if the true value is a 4 and it guesses a 9. Or if the true value is a 4 and it guesses a 0, it's going to apply a steep penalty. Whereas if the true value is a 4 and it gives it a 5 or a 3, it's going to apply a small penalty. And so what we want to do is we want to just say if it gets the wrong label, the penalty should be the same. Okay, and the only way we can do that is by having these kind of one-hot vectors, as you say, by saying if it's not that one category has a high value and everything else is a 0, it's going to get a bad mark. If in other situations where you have more of a regression output where you want to get, it's better to get close than it is to get far away, that makes a lot of sense. But in a case where you're doing classification where it should be you either got it right or you got it wrong, then this is the kind of the way we do it. Yeah.
I can see that.
Yeah.
Isn't it, right, in postcodes, isn't it better to be off by 1 than 9? And for visualization, in general,
no,
right?
well, in postcodes, well, it depends which one you're off by, right? Because you have 5 postcodes, 5-digit zip codes. If the last one is off, not that big of a deal. It's going to end up in the same state. But if the first digit's off, it's going to end up on the wrong side of the country type of thing. And yeah, so generally for classification things, we use like it's either correct or it's wrong type of thing. And so we set up our training data this way with zeros and ones, but when we train the thing, it's going to output things that aren't exactly zeros and ones. It's going to produce things that are like 0.02, 0.02, 0.99, 0.03, 0.01, something like that. So so it's still not a perfect thing, but that's the way the cost function works, is it says, what's the difference between the actual value and what we predicted. And so for classification systems, it makes the most sense to have it this way. Okay, so we have this. We write a function for the sigmoid function. With the derivatives, we write the function for sigmoid prime. We have our cost function here. Okay, apparently, I guess I had the thought when I wrote this that 150 is too many nodes to have in the hidden layer, so I'm going to say input layer 784, output layer is 10, hidden layer is 30. Okay, I'm going to set just some random values for my initial weight matrices. Okay, so it looks like kind of crazy code here. The random weight matrices, so our unif produces a random value between 0 and 1, and I'm asking input layer times hidden layer size, so 784 times 30, that's how many values I need in my initial weight matrix. So that's what that is. That's what it's doing. And then because it goes from 0 to 1, I'm going to just subtract half of a 0.5, so then it goes from negative 1/2 to positive 1/2. Okay, it's an arbitrary choice. I didn't have to do that. I guess I could have multiplied it by a random either negative 1 or positive 1, just so I get some a mix of values here. And so anyway, I set up my two weight matrices there. Here, B1, the bias matrix, is going to just be, in terms of, here I just have 30 in the hidden layer and 10 for the output layer. And then when I have to turn it into n by 30 or n by 10, I'll take care of that during the forward propagation step. But right here, for the bias matrix, just so that we only have this one set of 30 values and one set of 10 values, we are setting those up here with B1 and B2. Okay. So we're going to do stochastic gradient descent, and here I'm going to take my 60,000 rows. I'm going to split them up, and we're going to just sample from 1 through 10 there. Okay, so J sub, if we look at this, okay, just goes. Yeah, I guess I'm doing kind of, yeah, the first, we're just doing the first 10 and so on, and so forth. So here, what I'm going to do is I'm going to just take rows, J in 1 through basically the next one being 11, so 1 through 10 is what I'm doing. So we'll take, so the first one is going, it'll go from 1 to 1 plus 10, which is 11 minus 1. So 1 through 10, and the next one will go from 11 to 20, and the next one will go from 21 through 30, so on and so forth. Those are the rows that we're using for training. And then we subset training using that. I divide by 255 so that our numbers go on a scale from 0 to 1. Okay, and then we will use our vectorized labels here. We do forward propagation. We do x times our weight matrix 1. We apply the sigmoid function to z plus the B matrix, the bias matrix, and this is where I do b times repeating 1. Okay, so if I look at B1 right now is a matrix of 30, and what I want to do is 30 rows and 1 column. What I want to do is I want to turn this into n rows and 30 columns. So if I do B multiplied by matrix multiplication by, let's do 1 by 4, okay, it's going to give me the same value in 4 columns, and then I have to transpose that. So here now I would have 4 rows with those 30 columns, okay? And so in this case my batch size is 10, so I would have 10 rows with those 30 B values here. Okay, so that's going to be right here at A2. We multiply the output of that times the second weight matrix, and then we do the same thing. We add a bias, we apply the sigmoid function, and this is going to be our prediction y hat. Okay, we calculate our gradients, okay, which I kind of skipped the calculus for finding the gradient with respect to the bias, but it ends up just being delta 3 because you're just adding it, right? So anyway, it ends up being that thing. Okay, we calculate all of the gradients. Once we calculate those, we take steps in the opposite direction multiplied by the scalar, and we update that. So this is basically that's what we would do, and we can check some numeric gradient checking just to make sure our gradients are being calculated correctly. But I'll go ahead and I'll run that, and this just goes through the entire training data set of 60,000 one time. It's running right now, and now it's done. Okay, I'm going to skip the numeric gradient checking, but you can run through this on your own time. Okay, so we did all of that. It ran through all 60,000 rows. All it did was just went through the 60,000 rows in our training data just one time, and but we could do it again to improve the training, but we actually get decent results here. Okay, convert goes back from the one hot, so zeros and 1 back into the actual value. And so let's just kind of see how our matrix performs using the weight matrices we've trained. So we've got kind of our first weight matrix. These are the results that its font said was pretty good. Okay, we'll try out some of these in our test set. Okay, so x little t is our test data, and we'll just do some of this. Okay, and then we will so now that we have our weight matrices, we can do a forward propagation to get our y hats. Okay, so just so you can see kind of head of our y underscore hat, this is kind of what it looks like. The first output is times, everything is times 10 to the negative 7. This one's times 10 to the negative 3, and everything else is 10 to the negative 7. And then right here, here's one value that's 9.99 times 10 to the negative 1. So that's basically 0.99, and everything else is kind of on the order of 0.00 something, right? And then the next one, everything is very small except for this value, which is 9.1 or 0.91, and everything else is very small. And so we would so if I do turn these into guesses, okay, I would okay, so we would have a guess of 7, 2, 1, 0, 4, and 1. All right, and so let's these are our guesses based on our y hats. and let's compare the y-hats to the actual results. And looking at this, it's not too bad, right? So we have we had 85 instances of it being 0 when it was actually 0, and then it incorrectly guessed a 4, a 12, a 3, a 7, a few times. We have a bunch when it was the number 1, it guessed correctly 125 times, and it incorrectly classified it as a 4 once, and sometimes. And then, we have a few guesses of 12, 13, 16, or 17, and that's because it might have both, like, two numbers, like it might have had a 9 with a probability, like a guess, like a score of over 0.5, and a 3 with a score of over 0.5. And so when we did the rounding and add them together, because this function to get the results of all I did was just round, hoping that only one would round to a 1 and the others would round to a 0. That didn't always work out correctly, and so so sometimes they would add up, like a 9 and an 8 together would get something like 17. But you know, by and large, it's giving us decent performance. I mean, this was just running through the training set only one time, and not several iterations. And this is, again, just the most basic neural network where we just have one hidden layer. Okay, and you could choose to make a second hidden layer. It's just you would have to calculate some more kind of derivatives to say, how do I need to adjust the gradient to optimize the other hidden layer. But it's certainly possible, and that's how we would use it. R has some built-in neural network functions that allow you to kind of set up the neural network and train the neural network just using a few codes. But I think I know I just gave you a homework assignment, but I'll have a good homework assignment for this neural network stuff. And I think it is a good exercise to do some manual neural networking and all of this matrix and derivative and all of this kind of, can be a tiny bit painful at times. But I think that will help you get a better understanding of how the neural network works, how the gradient descent algorithm, which is really, really simple, but understanding how that back propagation in terms of calculating that gradient works. And then, once you are comfortable with that, then I would permit you to use the built-in neural network functions. But we don't want to just start throwing things into black boxes and have no idea how everything goes. There's lots of good resources online regarding neural networks. There's kind of this, I don't know what happened here. The CSS got lost. There's this kind of online textbook-ish thing called Neural Networks in deeplearning.com, and this work walks through the same thing of using the handwritten digit set. They start off using perceptrons. Don't worry too much about that. Then they go into sigmoid neurons and things like that. A lot of work has been done recently on neural networks, and again, we're not going to get into kind of the more advanced neural network stuff, but those longer videos that I've linked to, briefly mention some of the other changes. Like he says, the sigmoid function is a little bit outdated. I think it's still good and it's still very useful, but I guess when calculating derivatives, at some point it gets tough, and so they've used other functions and whatnot. So definitely, I think this is a area of interest that's worth trying to stay abreast about. But this is a good good introductory thing. So definitely read through. I'm hoping that the code I wrote for the artificial neural network and things will be clear for you to understand the example that we walked through, and also for the handwriting recognition, and then you'll have a homework assignment where you can kind of work through it as well. All right. Are there any questions before I let you guys go?
What is that BFGS thing?
Okay, so we have regular old gradient descent, and then in the video by Welch Labs mentions something called BFGS. So gradient descent just says which slope, where I'm standing now, what is the slope, which direction will give me the steepest slope, and we move in the opposite direction. Totally, that's fine, okay? BFGS kind of improves the gradient descent a little bit, but it also takes into account, I believe, second derivatives, and I forget, but it just takes into account a few other things before deciding on a direction to go. Okay, and so there's a bunch of algorithms for numerical optimization, right? So in calculus, you learned about finding local mins and local maxes by finding where the derivative equals 0. And then if you can't find that, if you can't solve for where the derivative equals 0, you can do things like gradient descent, where you just find the derivative at this point and then taking a small step. And then there's a bunch of other algorithms that try to find minimums and maximums in different ways. And BFGS is just one of many that gives slightly improved performance over straight vanilla gradient descent. But I forget all the details. You can look it up. And, yeah, it was mentioned in the video, and that's why I put it in the code. But yeah, I forget the BFGS optimization. Let's see. Broyden, Fletcher, Goldfarb, Shano algorithm. Everybody wants their name, right, in things. So this is the gradient, and I don't feel like reading through this right now. Obtain a direction by solving for this. Perform a one-dimensional optimization to find an acceptable step size. Oh, okay. So our current algorithm just takes step size. We just have this kind of alpha parameter or lambda parameter that says how big of a step we should take, and apparently this does a little bit more work to say, we can take a bigger step or a smaller step, depending on how smooth, if it feels like it's really steep, maybe we should just take a small step, but if it seems pretty flat, we can take bigger steps type of thing. So, okay. Anything else? Yes.
For the network, does adding more nodes, so not like another layer, but more nodes like the first layer, does that improve performance or like?
Generally, it allows. So basically, the more parameters you have in your model, you can generally reduce your training error. But the more parameters you have in your model also increases the risk of overfitting your data. But with neural networks, you just have tons and tons of parameters anyway, and so we just kind of arbitrarily choose like some decent numbers and throw it at there and see what happens. And we don't have a very great understanding of exactly what does it mean to just add one node. Like we can kind of see like, oh, if we add 100 nodes, like things change and things like that. But adding one or two, but you can kind of just play around with certain things and you can improve your error rate as such. by kind of messing around with how many things you have. Yeah, generally, you know, in our simple case, we just had one hidden layer, but probably a lot will have two hidden layers and things like that. Okay, we'll end here, and good luck on your current homework, and then I'll get another homework for this neural network posted, I don't know, at some point.